Hello, ladies and gentlemen. My topic is experimental and numerical investigation on the mechanism performance of an improved aluminum alloy joint. Aluminum alloy is a kind of lightweight, low-carbon, better mechanical performance in low temperature and environmental protection material. Based on these superior properties, aluminum alloy is suitable for aerospace, astronomy, and other occasions with special requirements. In the single-layer reticulated shear structures, aluminum alloy gusset joint as the most commonly used joint has attracted a large number of researchers to study. However, studies based on the traditional AAG joint remaining related to the mechanism under simple stress state. In this case, an improved AAG joint system has been adopted which was designed to show the better mechanical performance in a complex loading state. Beside the gusset plate and main post, three-direction core stiffener tube placed in the center is a new connector capable for transmit force and enhance the mid-web section to avoid its buckling. The L-shaped shear connectors placed between main posts smoothing the joint area to a large extent and transmit shear force between three posts. The empty space between gusset plates has a high probability of buckling that we add three I-shaped bearing stiffeners for avoiding. The most obvious difference between this joint and the traditional one is pie-shaped stiffener, which extend the joint area by connecting posts and gusset plates using short rib protruding from the section and smooth the joint area, avoiding stress concentration. The last component is H-shaped connector used for connecting posts and pie-shaped stiffener together and provide lateral support for main posts. A full-scale experiment of the improved AAG joint will be carried out to investigate its mechanical performance, especially the performance under complex loading states. The clarity of mechanical performance will enable the improved AAG joints to be extensively used in the fields of spatial structure and greenhouse buildings. To verify the test result, the improved AAG joint finite element model was established and analyzed in Abacus 2016. 747 bolts were taken into consideration in the finite element model, including plain bolts and ring-groove lock bolts. The material information from the material experiment characterized the material behavior in the finite element model. Hundreds of bolts produced a large number of surface-to-surface contact pairs, which might cause convergence problems. The general contact algorithm that required no penetration between each part was chosen, therefore. Based on the test and simulation results, we find the stiffness of improved AAG joint. There are three phases in the process of improved AAG joint bearing axial force. When the axial force is at the lower level, the loading pole bears the axial force and transmits it to the gussets. The adjacent pie-shaped stiffeners resist the load transmitted from gussets to make stiffeners beam columns afterwards. Meanwhile, the bottom pie-shaped stiffener also supports the gussets. That's why the first phase is called three-point supporting phase. As the axial force is increasing to cause plastic performance, the dominant load is resisted by two bottom poles instead. More importantly, the angles of these poles enable them to beat an arc when bearing axial force. We name this phase arc compressive phase. The in-plane bending behavior can be divided into four phases. The first phase is united bending phase, which shows elasticity performance. The loading pole can be regarded as a cantilever, hence the in-plane load is mainly transmitted to two near pie-shaped stiffeners by bolts averagely along invariant directions. When the section shows the plasticity completely, the plastic hinge appears, which leads to the second phase, plastic hinge phase. Simultaneously, another plastic hinge generates at the left pie-shaped stiffness. Before that, the curvature of it has disappeared because of the shear. Then comes the brief bolt fracture phase. The bolt on the left of the pole to connecting L-shaped connector and pi-shaped stiffener rupture firstly. Shear force transmitted by those bolts turn to others. Due to the loss of the support, the stress of plastic hinge on the loading pole decreases, which leads to rigid body rotation of the pole end. The performance on the resisting out-of-plane flexural force of the improved AAG joint is mainly aimed at in this research, which is also the purpose of the creating some of the components. The first phase of withstanding out-of-plane force is elastic bending phase. In this phase, the loading pole is supported by gussets in the main component to bear load. When the out-of-plane force exceeds to the ceiling of the first phase, a plastic hinge forms in H-shaped connectors. The stress of near pi-shaped stiffness stop rising therefore. We name it bending torsion phase because the bottom pole plays a role in resisting out-of-plane force instead. The loads passed to them are dominantly torque. If the out-of-plane force grows continually, the top gusset will buckle and lead to pole releasing phase. In the center section of the joint, only gussets themselves bear the load with the help of pi-shaped stiffness on both sides, and the I-shaped stiffness in it. That's all. Thanks for listening.